Okay, now we have this question, question one. In question one, it is column, I beam column, sorry, I section and column, I section column to subject to axial force of 8 kilonewton applied through the centroid of the cross-section area. Determine the average normal stress acting at section AA. Okay, so question one. Okay, we have I section. Okay. This is I section. This is the cross section of the I beam or I section. Okay. And we have applied load of 8 kilonewton is applied here somewhere in the centroid, 8 kilonewton. And given the dimension of the section, okay, I will draw here as well. This is the y-axis and this is the x-axis of the section, or this is x, y, doesn't matter. So if we look, the plan of this one will be something like that. This is our I beam. And the load will be applied here somewhere at the center line, at the centroid, 8 kilonewton. Given to us, the dimension is this 75 and 75 millimeter, all the dimension in millimeter. Okay. And we have the thickness of the web is 10 millimeter. Okay. The thickness of the flange as well, 10 millimeter. This flange as well, 10 millimeter. And we have this length or this height of the web is 140, and the load in the middle, so 70 millimeter. If we want to put this dimension here, so we have 10 millimeter, 70 millimeter, 70 millimeter, 10 millimeter, and in the other direction, 75 millimeter, and the thickness is 10 millimeter, 10 millimeter. The thickness of the web is 10 millimeter. Okay. Now we know the dimension and the applied load, and we need to know what is the requirement of this. We need to calculate the normal stress at section AA. Okay, and section AA is given at somewhere here. So this is section AA. Okay, what is the normal stress normal stress sigma, this refer to normal stress, is equal to the normal force N, represent the normal force, divided by the area, which is the cross section area. Okay, so we have our equation sigma equal to N by A, where N is the normal force, A is the cross section area. Okay, what is meant by normal force? Normal force is the force normal or perpendicular to the section. So any force perpendicular to our section or our cut, this is called normal force. And the stress resulting from this normal force is called normal stress. Okay? Is that okay for you? Okay, so now the first step is to know what is the normal force on section AA or at section AA. Anyone know what is the normal force at A? If we are at AA, if you make any cut in a structure, this cut divides the element or the member to two parts. So we have one part from top and one part from bottom. So if we study the top part, what is the normal force on section AA? The normal force is any force perpendicular to section AA, which is 8 kilonewton. So the normal force we have here is only 8 kilonewton. Okay? Do you have any question? Okay, this normal force can be compression or tension force. Any normal force can cause tension or compression. Okay? If the force is, if we have a member like that and we are pushing this element, so this member is under compression. If we have a member and we are pulling this member, so this member under tension. So for our example now, under compression or under tension? Yeah. Right, Jian, it is under compression. Because if you look at section AA, the force 8 kilonewton is pushing to AA. So this force is compression. We give the compression negative sign, and the tension positive sign. So this force 8 kilonewton cause compression, and we give it negative because it's compression. Okay. So now we know the normal force. The second step is to know the cross section area of section AA. What is the cross section area of AA? The cross section area at AA is the cross section area of the I section. So if you calculate the area of the I section, so you get the cross section area. How can we determine the cross section area of this I beam or I section? Can you help me with that? We have, if we divide it, we have three parts. The flange here, the black flange, and the black flange here. So this is 1, 2, and we have the web, which is area 3. So if we sum the area of 1, 2, 3 parts, so we can get the cross section area. So we will do like that. We have any one of the flange is 10 millimeter is the width multiplied by 150. And I will multiply by 2 because they are two flange. Plus the web. What is the area of the web? 140 by 10, which is the area of web or area 3. So this is area 1 and 2, and this area 3. From this equation, we can get the cross-section area of the I beam. Okay, so we will have 1 multiplied by 10 multiplied by 150 plus 140 by 10 give us 2900 millimeter square. So this is our cross-section area. Okay? So now the last step is to find the normal stress sigma. What is the normal stress? Normal stress will be normal force over area. So we will have negative 8 kilonewton divided by 290 millimeter square. Okay? It is preferable for us to use Newton and millimeter. The units are Newton and millimeter for this type of problem. To convert kilonewton to Newton, how can we convert kilonewton to Newton? If we multiply kilonewton by 1000, this gives us Newton. So it will be sorry, the area, there is a problem in the area, 10 by 150. Okay, I forget the 2. Okay, this number just need to adjust. Thank you, Gong. This number is 4400. Okay, so the area is 4400. So you will put here for 400 millimeter square. Okay, now 8000 negative divided by 4400 will be Newton by millimeter square. This gives us the final result of the stress will be negative 1.818 Newton per millimeter square. Okay, is this answer correct? Do you have any problem with this one? Okay, what does this negative mean? This sign mean this section is under compression or tension? Compression. Okay, so that's it for question 1. We have done the stresses, normal stresses. So I will pause the recording now. Okay, for question 2. We have a column with with variable cross section. No, I know the number is not correct, GN. Okay, now I will start doing it. We have a column. This column has a variable section. It is supported at the base here. Whatever the shape. Okay, we have one applied load at the top here, 5 kilonewton. And we have two applied load here, 3 kilonewton and 3 kilonewton. Okay. Sorry, what you mean by the force analysis launching? I will just continue drawing the example, and we have this called point B. At the top is B, and this part is C, and the support is D, and we have here somewhere point A. Point A is in the middle of this part, which is 1.2 meter. And we have the top part is 3 meter. Okay, this is the shaft we have or the column we have. The requirement is to determine the internal normal force at point A. So we need to know the maximum normal force at A, where giving you another or more information. Segment BC weights 300 kilogram per meter length. Segment CD weights 400 kilogram per meter length. Okay. So this is the forces we have, and our cross section will be somewhere here at A. So we need to calculate the normal force only at A. The normal force, again, we said in the last example, normal force, we give it the symbol N, and the normal force is the force perpendicular to section, to our section. So what is the forces causing normal at A? If you have any answer for that. Ronching, do you have answer? Yes, 11. We have 5 kilonewton going down, 3 kilonewton going down, 3 kilonewton going down. All these three forces are perpendicular forces on the section at A. So theoretically, we have 5 kilonewton, 3 kilonewton, 3 kilonewton. This is the forces causing normal. Do you have any idea if there is any other forces acting as normal forces for section A? What about the weights of this part? If this part, yes, good. If this part has weight, so this weight should be included. So if I will write a small hint here, if weights can be determined or can be calculated, you should be included. Okay. So if you have enough information about weights, it should be included in our calculation. Okay. So why it was not included in the previous example for the question one? Why no weights? Because there was no information about the weights in example one. But here, because it is giving that segment BC weights 300 kilogram per meter and CD weights kilogram per meter, 400 kilogram per meter. Okay, so the weights of member or part BC, I will call it WBC, and the weight of this part, which is part AC, should be included. So I will add two weights here, WBC and WAC, to the calculation. How can we calculate WBC? How can we calculate the weight of part BC? It is giving to us as uniform load 300 kilogram per meter. But we need to get the total load of this part, so we need to multiply this part by the length of this part, LBC. What is the length of part BC? 3 meters. So we need to multiply it by 3 because this one given in kilogram per meter. So each 1 meter weight 300 kilograms. So the 3 meter weights how much? 900 kilogram. Okay. So this will be as concentrated load 900 kilogram. Okay, same, we will do the same for member AC, which is how much is the length of member AC? This light green one? Yes, it will be 400 kilogram per meter multiplied by the length of member AC, which is 1.2 meter. This will give us the result as 480 kilogram. Okay, so the weight here of member AC equal to 480 kilogram. So now all the forces are given or are known now for member for this column, or we need to do more calculation? What do you think? Now, is there any loads could cause normal force or normal stresses at section AA, or this is the forces we have? So we have 900, 3 kilonewton, 3 kilonewton, 5 kilonewton, and 480 kilogram. Okay, so this is all the force. But there is a small trick here. Do you know what is the trick here? Do you know what is the trick here? The normal force, the final normal force will be summation of all normal forces applying in this or acting on section AA. So it will be 5 kilonewton plus 3 kilonewton. I will write the unit. Plus 3 kilonewton plus 900 kilogram plus 480 kilogram. Is this logic? Can you sum kilogram to kilonewton? Is that logic? No, you can't. This is wrong. If you do this, so you will get maybe 0 in this example or half of the mark, because you can't sum the kilogram with the kilonewton. So what we need to do first is, I will remove this part. We need to convert the kilogram. So we need to convert kilogram to kilonewton. How can we convert from kilogram to kilonewton? We have 2 steps. Just you need to keep this in mind. You know that 1 ton, or let's say in different way, 1000 kilogram is equal to 1 ton. So if you want to convert from kilogram to ton, you need to divide by 1000. Okay. The next step is 1 ton equal to 10 kilonewton. Okay, so now you know that 1000 kilogram equal to 1 ton, 1 ton equal to 10 kilonewton. So 900 kilogram is equal to 0.9 ton after dividing by 1000. Then 0.9 ton is equal to 9 kilonewton after multiplying by 10. Similar here, 480 is 0.48 ton. Then multiply by 1000 by 10, it will be 4.8 kilonewton. Okay, if you want to merge these two together, so we have finally 1000 kilogram equal to 10 kilonewton. So 100 kilogram is equal to 1 kilonewton. So if you want to convert from kilogram to kilonewton, what you need to do? Divide by 100. Okay, so we have two ways to do it, like one from kilogram to ton, then from ton to kilonewton. Okay, what is the last step in this problem or this example? The last step is to sum all this normal force. The normal force, the total normal force will be 5 plus 3 plus 3 plus 9 plus 4.8 will give us how much? 24.8 kilonewton. Okay, do you have any question for this one? Do you have any problem? My last question for you is this force compression or tension force? If you have a look again to the example, tension or compression? Compression. Because if you are at A, here, all the forces pushing to A, so this force is compression force. So I will give it a negative sign. So this negative means this force is compression. Okay? Do you have any question for this one? No problem? Okay. So for this question, just share the screen again. Can you see my screen now? Okay, so for this example, we have a shackle, anchor shackle is supported by a cable with a force 3 kilonewton. So we are in question 4 now. We have this shackle, something like that. Okay, and we have a pin or a bolt somewhere here. In black. The thickness or the diameter of this one, of this pin is 6 millimeter. This means the cross section of this one is a circular and the diameter of this circle is 6 millimeter. And we have a cable or a rope is hanging like that. And the force is in this rope is 3 kilonewton. Okay. So we have the force equal to 3 kilonewton. The diameter of the pin is given as 6 millimeter. This is the knowns, or this is the givings. And the requirement is to calculate the shear stress in the pin or the bolt. Okay, how can we solve this problem or this example? If we simplify this to a structure model, we will have the pin or the bolt as a line like that, and we have in the middle here a force 3 kilonewton. This pin is supported by the shackle itself, which is, we can represent it as two support like that, and this two support will hang the rope. So we will have two reaction if we call this A and B. So we will have YA and YB. Okay? Do you agree with that? So we have force 3 kilonewton going down, and the shackle itself support the pin from two nodes or 2 points. So we will have two reaction YA and YB. Can you expect how much YA and YB? YA will be equal to YB will be equal to 3 kilonewton divided by 2, because this force in the middle, so half go to the right, half go to the left. So the reaction at A and B will be 1.5 kilonewton. Okay. If we have a look here, so we will have 3 kilonewton, 1.5 going up here and 1.5 going up here. Okay. So we have three forces now. What is the shear? Which one of them causes shear? If you cut here at section A and here and here, if you want to draw the shear force diagram for this one will be, if we go up with YA, we will go up to 1.5 kilonewton and then go straight up to the force 3 kilonewton. Then we go down 3, so we go down to 1.5 kilonewton, then go straight and then go back to 0, this positive and this negative, and we call this the shear force diagram. Okay, we will go through this in detail later in the course, but if we cut at A, the force that cause shear will be YA. So the shear force, we can give it the symbol Q capital or V. So the shear force in this example is equal to 1.5 kilonewton. Okay, and the requirement is the shear stress. The shear stress, we give it the symbol Q small, shear stress, and any stress is equal to force by area. So because this shear stress, it will be shear force. So if we divide the shear force V over the area A, so we can get the shear stress. Okay, so this is our formula now. Q equal to V by A. So how much V? We know V as 1.5 kilonewton. Divide by the area. What is the area of this example, of this bin? The area is the area of circle. The circle area is by D squared by 4, where D is the diameter, and or by R square if R is the radius. In this problem, we have the diameter or the radius. In this example, we have the diameter or the radius. The diameter. So the area for this example will be by D, which is 6 squared divided by 4. Okay. So now we have, and the area will be in millimeter squared. We have a small tip here. It's better, as we said before, to study or to get the units in Newton, Newton and millimeter. To get the result in Newton and millimeter, we will multiply 1.5 kilonewton by 1000 to be in Newton, divide by the area by 6 squared divided by 4. This will give us 53.08 Newton per millimeter squared. Okay, so for this example, this shear stress, because why is this called shear, not normal like the previous example? Because the shear, if this is a cross section or this is a cross section, the circular cross section, the forces are parallel to the section. If the force is parallel to the section, this means this force causes shear. And the shear stress will be the shear force divided by the area. And we have the shear force is 1.5. The area is area of circle by d squared by 4 divided by 4. So the final result will be 53.08. Okay. Do you have any question for this example? You have any question? Okay. So now I will stop sharing now. This one. We will shift to week 2. You are seeing now week 2. Can you see week 2 problem now? Okay, for this week 2, we will have a little bit harder problems because we will include the materials or the material properties to make the complicated ideas a little bit. Okay, but before we go through, I have two reminders for you. The first one is, one reminder. The reminder is that next week we will have a quiz at the end of the class. So please all of you attend because there will be a quiz, and the quiz will be with some of the marks of the total marks. So all of the class need to attend, and it will be at the end of the class. Okay. You have any question about the quiz? The quiz will be from the tutorial example and the lecture examples. I think maximum two questions will be in this assignment, and it will be from the tutorial and from the lecture. And all the solution for the example in week 1 and 2 questions will be available, or it is now available on the website, so you can have a look on them to practice for the exam or the quiz, sorry. Okay, so next week will be quiz, and try to be ready for it. Okay, any other question for the exam? For the quiz, sorry. Okay, now I will solve an example with you related to questions in week 2, and you will do the week 2 question yourself. So now, if you see my screen, can you see my screen now? Okay, this is the example we will do now. In this example, we have this type of truss or two link members connected at B and supported at point A and C, and we have unknown load applied at B, and we need to find this unknown. And it is given to you that this material, the material of this truss is polystyrene, and the strain diagram, which is the material properties, are given in graph. In this graph, we have two curves, if you can see, curve for the compression, behavior in compression, and curve for tension. So we have two graphs. Okay, and given as well the cross section area of bar AB and bar BC is 950 and 2500 millimeters squared. This is also given to us. Then the last thing or the requirement is how much is the largest B that can be applied to this structure before rupture, before member rupture. Okay, and we have assumption that no buckling occurs in this example. Okay. Do you know what is required now? Do you have idea how to start this one? Anyone have idea how to start? No idea? Okay, for this type of examples, for this type of problems, we will share the screen. Now we have exercise 2. For this example, we have 2 parts. The first part is the structure itself. We have this truss. This is like the truss we have done last week and the truss project, but small one. So we have 0.9 meter and 1.2 meter, and we have applied load somewhere here, which is unknown, B, and this node called A. Sorry, this one A. This B, and this C. Okay, so this is the structure we have, and given to us the area of this member AB is 950 millimeter squared, area of AB, and the area of member BC is equal to 2500 millimeter square. Okay, and given to us as well 2 curves. This for tension, this sigma, the stress in MBA, and the strain millimeter per millimeter because the strain unitless. So this is the tension. The maximum tension is 35 megapascal. This is the maximum tension. And if you have a look on the compression, it is like that. Okay. What is the maximum for compression? This is the behavior in compression. The maximum of compression is here 175 megapascal. And because it is compression, should give it a negative sign. So from these 2 curves, because no buckling will happen, we will assume no buckling happen to our structure. So if maximum allowable for this material in tension, which is the maximum stress this material can carry in tension, is given to us as 35 MPa. This is what we can conclude from this figure. And if maximum allowable in compression will be negative 175 MPa. Okay, this is all the information we know. To solve this problem, we need to understand that we need to firstly find the normal. Our first step is to find the normal force in members AB and BC. This is our first step. Okay, But I will ask you a question. Can anyone give the value of or the exact value of member AB or BC now, or we can't? Can we do this as the first step, or we can't? Do you have idea about that? Okay, because B is still unknown for us, so we have 3 unknowns now. So we can only get the force in member AB and BC in terms of B. So we will get the value of AB in term of B and the value of BC in term of B. This is the first step. The second step is to calculate the normal stresses for member AB and BC. How can we find this step? Sigma equal to the force in each member divided by the area of each member. That's why it is given to us these two values. Okay. The last step is equalize these stresses with max, because the stress in member AB shouldn't be more than the allowable stress of the material. If the stress is less than, if sigma AB less than the allowable stress, this means this member is safe. If the stress in member AB bigger than or larger than the allowable stress, this means that this member will rupture. Okay, so to ensure that this member will not rupture, we need to assume that the stress in member AB will be equal to the maximum allowable stress of the material. This is the first step or the first assumption. Similar to member AB, we will do the same for member BC. Sigma BC as well should be not more than the allowable maximum stresses, because if sigma BC less than the allowable, this means the member is safe. If sigma BC greater than sigma allowable, this means that this member will be ruptured. Okay, so we have two stages here. Sigma AB should be equal to sigma allow max, and sigma BC should be equal to sigma allowable max. From sigma AB and sigma BC, we can find the value of B or the unknown B. Okay. Do you have question about the steps of this one, of this question? Any problem till now? Are you still here? Okay, any problem? Can you understand the steps? Because I will just I will follow these steps now. Okay, this problem has a trick because it doesn't give you the requirement directly. It give it like with some we need to do some calculation first to get the requirement. That's why it is a little bit tricky. Okay. Okay, now I will proceed to solve this example. Okay, now we will divide it like that. So we have here this is our truss, this member A, B, C. How can we find the forces in member BC and AB. Similar to what we have done last week, if we cut here, we will assume that the force in member BC is tension and called FBC, and the force in member AB is also tension and we call it FAB. Okay, and then we will study the equilibrium of joint B. If we study the equilibrium of joint B, so this is joint B. In joint B, we know that we have a load here, B, unknown. We have the force here, FAB, and the force here, FBC. How many equations we have at joint B? Two equations, summation x equal to 0, summation y equal to 0. Okay, so to proceed in this problem, we need to get all the force in horizontal and vertical components. So all the forces should be horizontal or vertical. Okay, so now we need to analyze the force FAB. How can we analyze this force? If we take this triangle here, so this is our triangle, and this is theta. So this is our angle theta, and this is theta. Theta, we know this is 0.9 meter and 1.2 meter. So to get the hypotenuse, how can we get the hypotenuse? The hypotenuse, I will call it, let's say x. X will be the root of 0.9 square plus 1.2 square will give us 1.5 meter. So this hypotenuse will be 1.5 meter. Okay. So if you know the opposite and the adjacent and the hypotenuse, so now we know that sine theta will be the opposite 0.9 over 1.5. Cosine will be the adjacent 1.2 over 1.5. So this one will be 0.9 over 1.5 will be 0.6. And 1.2 over 1.5 will be 0.8. Okay, so can you tell me how much is the horizontal component here and how much is the vertical component? The horizontal component will be FAB, sine or cosine. This component is near to the angle, so it will be cosine theta. And if the vertical component will be the far component, so FAB sine theta. Okay, if when we replace cosine with 0.8 and sine with 0.6, these two components become 0.8 FAB and 0.6 FAB. Okay, and now no need for the force itself now. So we have two components, vertical and horizontal, for the force. Okay, now we can apply the two equations. If we apply summation x equal to 0, how many forces in x? Two forces in x, FBC and 0.8 FAB. So we have FBC negative because it goes to the left, minus 0.8 FAB because it also go to the left, will equal to, sorry, I will start from I will just delay this one first, delay this one. Okay, I will start with equation y first. Sorry, it will not affect too much, but just to make it easier. So if we start with the equation y, summation y equal to 0, what is the forces we have in y direction? In y direction, we know we have B and the vertical component of the inclined force 0.6 FAB. So we have B going down negative minus 0.6 FAB going down should be 0. From this equation, we find that FAB equal to minus B divided by 0.6. So FAB is negative 1.666B. And I will call this equation 1. So equation 1, we get that FAB is negative 1.666 from B. So this is what we called it. We find the force in FAB in terms of the unknown. Okay. If we apply the second equation, summation x equal to 0, we know that we have negative FBC and negative 0.8 FAB should be 0. Okay. From equation 1, I will move or remove FAB and replace it with negative 1.666B just to get FBC as well in terms of B. Okay, that's why I start with Y equation. So from this equation, we will find that negative FBC negative 0.8 multiplied by negative 1.666B should be 0. From this equation, these two together will give us plus 1.333B. So FBC will be positive 0.1333B. And I will call this equation 2. So now, after this calculation, we know that we have two equations and two information now. FAB is equal to negative 1.66B and FBC is equal to positive 1.333B. Okay, what does that signs mean? The negative sign mean tension or compression, and the positive sign. The negative sign means that member FAB is under compression because it is negative, and the positive sign in member BC means that the member is under tension. Okay. So member AB under compression, member BC under tension. So now we finish the first step, which is getting or determining the forces in AB and BC in terms of B. Okay. Now I will go to the second step, which is the stresses. The second step is to get the normal stresses in the member. Okay. Again, the force in member BC equal to negative 1.666B. The force in member AB is positive 1.333B. And what else we know here? It is given that the area of member AB equal to, or BC first. Member BC is 2500 millimeter square. Area of member AB is 950 millimeter square. Okay, so the stress in member BC will be equal to negative 1.66B divided by 2500. Okay. How can we get B now? This is the stress in member BC. As we mentioned before, to make this member safe, sigma BC should be less than or equal to F allowable maximum. Okay, but we have two values, tension and compression. Which one to choose? This is my question to you. To get the value of B, we need to equalize this stress to the maximum stress. Which one to equalize? I'm waiting your answer. The tension or compression? So I will make it easier for you. This member is under tension or under compression with the negative sign here. Under compression. So if it fail, it will fail under compression. So to get the values, we need to equalize sigma BC will be equal to F allowable maximum in compression. If you go back to the example, this value was negative 175 MPa. So now sigma BC is equal to negative 1.666 B divided by 2500 should be equal to 175 MPa. This is Newton by millimeter square. This is Newton. This is millimeter square. So now the only unknown we have here is B. We now can get B. B will be equal to, if you make the calculation, 175 by 2500 divided by 1.666 give us sorry, there is something wrong here. I will go back to the last step. Okay. So we get something wrong from the last step. Okay. I know now what is the problem. Okay, from last step here, FAB was, I just replace AB with BC. Okay. So member AB, FAB is negative 166B. Member BC is positive 1.333. Okay. So again here, sigma, this is sigma AB should be negative 1.666 and the area of AB is 950. Okay. So from this calculations, it's 950. The force and member AB, B from AB, sorry, just remove this. Now I will call this B coming from member AB because we will have two values. So B from member AB will be equal to 175 by 950 divided by 1.666 give us 99,750 Newton. Why I put the value in Newton, not in kilonewton? Because here you have Newton and millimeter square. Millimeter square will cancel millimeter square, so the remaining will be in Newton. So if you want to make this value a little bit smaller, we can divide by 1000, so it will be 99.75 kilonewton. So this is our first value of B. We will do the same for member BC. For member BC, we know that sigma BC will be the force in BC, which is positive 1.333 B divided by the area. What is the area of member BC? 2500 millimeter square. Okay, this member is under tension, so we should know that member BC the stress in member BC should be less than or equal the allowable maximum stress in tension. Why the allowable maximum stress in tension? Because member BC is in member AB, or member BC is in tension. Okay, because of this sign here, tension. So this member is in tension. So sigma BC should be equal to 1.333B divided by 500 millimeter square should be equal to plus 35 Newton per millimeter square. Okay, from this equation, we know that B will be equal to 625 Newton. Okay, and to make it smaller, we will have to divide it by 1000, so it becomes 65.62 kilonewton. This is the value of B. So we have two values of B now. Okay, value of B from member AB, value of B from member BC. So what is the maximum value of B for this example? Which one to pick here? The smallest or the largest? The smallest. So B, to be safe for both members, B will be the smallest of the two values, which is equal to 65.625 kilonewton. So the final result is 65.625 kilonewton, the smallest one, because the smallest will be safe for both of them. But if you use the bigger one with member BC will rupture earlier, so it will be unsafe. Okay, so this is example for how to use the material properties in the normal stresses to get the requirements, and you can try. I will share with you. Okay, you can try week 2 examples here. You have 4 examples, you can try them, and the solution for this example are on the Learn Online website. So you can try them and have a look on the result. Okay. And the scope of this quiz 1 is what we have done up to now in the lecture and in the tutorial. So mainly trusses and normal stresses and shear stresses. And it will be example from the tutorial or the lecture. Okay, so have a look on them and try to practice them, and hopefully you can solve them easily. Okay, any other question for today? Any other question? Okay, all good. Do you need anything from me? Please inform if you have friends that they didn't attend today or before. Please ask them to join next week to attend the quiz. Okay. Why the quiz is in the quiz is on the next class Friday. Our class guide is on Fridays from 3 to 5 Adelaide time. Okay. Not in the lecture. I don't know if the lecture is Wednesday. The quiz only 15 minutes or maximum 20 minutes, but I mean the class, our class from 3 to 5. But the quiz, it is not an exam. The exam is not 2 hours. It's only a quiz. So the quiz is short exam, only two questions, and we will do it at the end of the class. Okay. Any other questions? For project one, you need to start doing it with your mates. As I mentioned, you have the load case now and the group members, and each member of the group need to analyze and get the forces in 3 members. And you have the due dates. I don't know if it is next week or when. So please check the due date for the truss example so that you can submit it before the deadline. Okay. Yes, you have to check the result with software, the space gas. What you need to do with the space gas is you have the links of your truss and you just add the load at your point. So Zingma has already prepared the model, so you just need to insert the load and then get the result and compare it with your result. 2 questions for the quiz. 2 questions for the quiz. And both questions are from the lecture notes or the tutorial. Okay, just try to practice as much as you can, so it will be easier. No problem with the quiz. It is easy. Just to make you update. Go with the lecture. Don't leave something behind you. So you know what you have already done and what you have. What is the problem you have, so you can improve. Okay. Any other question? Okay, guys. Thank you.